So, anybody want to take a stab at what probability is?
I said the likelihood something will or will not happen.
So I would say so the likelihood of a given outcome.
Likelihood something will or maybe will not happen. Okay, likelihood of a given outcome. Okay, use likelihood also. Okay, that's cool. Okay, not got anything different.
I just put chance instead.
You use the word chance.
I said the
Okay.
chance of getting a certain outcome.
Outcome. Okay, so they all have similar things. Another idea about probability. It's a measure of your belief that something will happen. So the question is, how do we measure that belief? So I handed out some cards earlier. We all got a red card, which seemed a little unusual, right? So it was kind of straining my belief system there about cards because half the cards are supposed to be red. Right? And half the cards are supposed to be black. So if I start dealing a bunch of cards and they keep coming out red, this is starting to challenge my belief. Yeah.
But it still challenges the one you're shuffled.
Well, yeah, there's lots, so it could happen for a variety of reasons. It turns out I have a stacked deck. Okay. Like mostly red cards, 2 black.
The point is that you start to think that something is up.
Yeah.
These cards must not be shuffled.
Yeah, so it really is a measure of belief, and there's a lot of things that go into that belief. So we're going to talk about measurement and belief today for probability. So how do we measure probability? That actually isn't that hard to begin with. The measure is just a fraction, and it is favorable outcomes in the numerator and total outcomes in the denominator. So, for example, I looked at that deck of standard cards. And I got a red card, and I envisioned what I know to be a deck of cards, and so I want to look at the probability of getting red, which I got. And so with this idea of, let's see, there are 52 cards altogether, so that's my denominator. And half of those are red, that's 26. Or maybe I just remember half of them are red, and I just think 1/2 right away. So there's different ways to come up with that measurement. I could call it 26 out of 52. I could call it 1/2. Jackie called it 50%. As a decimal, 5/10. So there's many ways we can state that measurement. Which is the better answer? I got 4 different answers for that probability of drawing a red card. Is there a best answer? They're all equal, right? So last chapter or the chapter before, right? You might have gotten lost a point because you didn't reduce your fraction. With probability, I think a lot of times we don't want to reduce because if I don't reduce, I can see what the total outcomes are on the bottom, and that's kind of nice sometimes. So often when I'm playing with probabilities, it's a matter of counting to find the favorable outcomes, counting to find the total outcomes, and then you could state that as a fraction or a decimal or a percent. So I usually go for the fraction, if I can come up with it, and the percent. So I usually state it in 2 different ways when I'm playing with them. The fraction is nice for me because it reminds me how I got the answer, and the percent is what most other people want to see. Okay, so belief is another part of this, right? So as far as the card example goes, as far as cards go, how did my beliefs fit into that? Well, I believe there were 52 cards. Right? I believe that half of them were red. Basically, I have this picture in my head. Steal this picture from here. I believed this. Right? I believed there were 52 cards. I believed there were a bunch of hearts, and a bunch of diamonds, and a bunch of spades, and a bunch of clubs, 4 aces, 4 tens, and so on. Okay. So as long as my beliefs are right, then I should be able to measure the probability. Okay. Are our beliefs always right? Not necessarily. Okay. So one thing we have to do is we have to learn to question our beliefs when we're trying to calculate probability. Sounds like a weird idea, belief in math class, but it's true. Okay. So let's look at another example where we have to consider beliefs. A coin. It's popular to flip coins and look to see if you get heads or tails, right? So if I have one coin, you guys mentioned the idea outcomes. Outcomes is something or some things that can happen. Like a red card is an outcome. The ace of spades is an outcome. Heads is an outcome, right? So an outcome could be a bunch of things grouped together or a single individual thing. So outcomes versus simple outcomes. So like a red card is an outcome, but it ain't simple because there's a bunch of different red cards. A head, on the other hand, is not only outcome, but it's a simple outcome because I can't break heads down any further. Right? It's just, there's a head. On the other side, there's a tail. What if, like the cards, I talked about the ace of spades. Is that just an outcome or is it a simple outcome? It's a simple outcome because there's a single ace of spades, yeah. So something simple if you can't break it down. Like a red card, I can say, well, there's the ace of hearts, and there's the 2 of hearts, and there's the 3 of hearts, blah, blah, blah. Then there's the ace of diamonds and the 2 of diamonds and so on. So if you can break it down further, it's not simple. Often we're interested in simple outcomes, but a lot of times we're interested in groups of outcomes. So the simple outcomes for a coin are either a head or a tail. The simple outcomes for the cards was that picture of all of the cards. Each card is a simple outcome. Okay, so coins. I've got some coins. I don't have any in my pocket. I've got some fake plastic ones here. Make sure that has a head and tail. Okay, so those coins have heads and tails, right? So we flip a coin, and we want to find the probability of getting a head. Now, that's a lot of words. So usually we abbreviate things like this. Like here, I would abbreviate that as P parentheses H. So that's my shorthand for probability of a head. With the card example earlier, I might write P parentheses red. Like a real coin instead of plastic. I don't know. Yeah, it doesn't feel the same. All right, I just flipped and I got a head. What's the probability of getting a head? 50%?
Yeah, 5/10.
5/10. 1/2. Okay, so those are all great examples of this right here. 1/2 is nice because there's one outcome. It's a head. There's 2 total outcomes, head or tail.
Does it matter how many times you flip it though?
That's a whole nother idea about probability we're going to get to in just a moment. Okay, let's get to that idea. Let's switch to a different scenario. free throws. Okay, so. So I've got this ball. And I'm going to shoot it into the basket, right? How many outcomes are there here? It's either in or it's out, right? I throw it, it goes in. I throw it, it didn't go in. Two things can happen. Kind of like with the coin. Two outcomes. What's the probability I get it in? 1/2. Okay, so a friend of mine's gonna take me to a Blazers game, and probability it goes in is 1/2. So I say, hey, I'm as good a shot as anyone here because the chance I'm gonna get in is 1/2, and they're gonna let me on the team, right? And shoot free throws? No. Do you think they're gonna do better at shooting free throws than me? And the probability is probably not 1/2. Aha. So belief again. It comes back to belief. So going back to the coin for a minute, we'll come back to the free throws. There were some beliefs that led us to the 1/2. What were those beliefs? Okay, so coin, beliefs. All right, so beliefs, there's a head. And there's a tail. Jackie said fair. What do you mean, oop, tail? Sorry, I got confused. My mouth with my hand. Jackie said the word fair. What does that mean?
Means because they have two-headed coins and stuff like that in the magic shop, so
Okay.
I would know it's not one of those.
Yeah, that would mean you always get a head. Okay.
This is a Mount Rushmore coin. So.
Okay. There's a head on both sides. Yeah, that's kind
Or
of.
it could be weighted to always land on.
Yeah, one
side.
side. Like think about toast with butter on one side. If you drop the toast, it's probably going to land on the butter side. Okay.
Or like a cat.
Okay, yeah, cat's a little bit different. We get a lot more going on there. But the idea of fairness means that each outcome has the same chance of happening, right? So we have outcomes with equal probabilities. That's a belief we have. Is it true? I don't know. I'll flip the coin 1,000 times and maybe I'll get 500 heads and maybe I'll get 500 tails. Even if it's fair, I'm not guaranteed to get 500 heads and 500 tails. That's not what probability means. That's another idea we'll get to shortly. Could it land on its edge? So there's kind of a third side to a coin. There's the head, the tail, and the edge. Now, a lot of coins, it's very hard to balance it on the edge. So having it land there seems pretty unlikely. So we can give that likelihood back to the head and the tail. But it's possible. It's in the realm of possibilities. It's just unlikely, right? It's right up there with me getting to the NBA. Okay. It could happen, but it probably isn't going to happen. All right. So as far as the free throws go, my belief structure for probability and the way I measure it doesn't directly apply here. Okay. I can't just look at this and say, oh, right, it's not 1/2, it's 30% to 70%. I don't know. I need data. Okay. So the coin kind of problem, the card kind of problem, if we play with dice, those are all what we call theoretical probabilities because we're pretty sure our belief structure about them is correct. Okay. But the free throw, I need some more details for that belief structure. So that leads to a kind of probability called experimental probability. So with experimental probability, we have what are called trials. And a trial is where you run the experiment. Well, the experiment is I shoot the ball and we'll see if it goes in or not. Okay. So trials are experiments. And then we just repeat the experiment or trial over and over again. And in the case of the free throw, a favorable outcome is I'm hoping to get it in, right? The other team's hoping I don't, so favorable is a matter of perspective. But the probability is still going to be similar to before. It's going to be the count of favorable outcomes divided by total outcomes like before. But I have to experiment over and over to see this happen. I can't just look at the situation and believe it's going to be something. So each outcome comes from running a trial, and I have to do this over and over again. And there are some probabilities that we have to do experimentally, and there are others that we can look at and get a pretty good idea theoretically what's happening. So we have two kinds of probability. We have the experimental, and we have the theoretical. They're both measures of belief. They have the same fraction, but to count the numerator and denominator, we have to do slightly different things. There are other kinds of probability out there in the world. Okay. For example, we had a late start today because we had some precipitation. Right? So often when I look at the news or the weather, I see that there's a chance of precipitation. Okay. So I'm kind of curious. Somebody told me it was going to snow tonight. Anybody hear that?
Yes.
So let's look up weather, and let's see. I got some. What's that?
A 70% chance of winter.
Of winter events. All right. So let's see. Today is Wednesday. There is a 70% chance of precipitation. So that is a probability. Okay. So we have another version. So let's just call this other probability. A friend of mine called these EWAGs, or educated wild ass guess. So 70% chance of precipitation. What does that mean? It's going to snow in 70% of Pendleton. So there's 30% of Pendleton that won't get no snow? Nope. Does it mean 70% of the day we will get snow, the other 30% we won't? No. What my interpretation of this is kind of related to quantum physics. Quantum physics has some weird stuff in it that we can't, one of the interpretations is that anytime a decision can be made about what particles can do, one thing happens in this universe and the other thing happens in some alternate universe. Okay, so you get this alternate universe theory. So the way I look at it is there's 100 different universes out there right now that have the same conditions as we have now. In 70 of them, it will snow, and 30 of them, it will not. Okay. And I'll talk more about my alternate reality, alternate universe in probability, because I use that idea a lot. It helps me think through it. So this is not, did somebody go and run thousands of trials with the weather conditions here and write down, oh, look, it snowed today. Oh, exactly the same conditions, it didn't snow today, right? There's some of that, right? We record weather data, right? So there's some of that experimental stuff going on in here, okay? But there's also some belief structure going on based on what we know about science and the atmosphere, okay? So there's some theoretical stuff here. There's some other experimental stuff going on here. But then there's a computer running in the background trying to generate alternate realities and see, hey, did it snow? No. Did it snow? Yep. Did it snow? No. Did it snow? Yep. Right? It's a computer system, like a video game running in the background, trying to take the current weather conditions and say, hey, is it going to snow in an hour or not? Sometimes the computer model snows, and sometimes it doesn't. So this is a little more complicated. It's a blend of a couple of different probability models and it's technology altogether, trying to figure it out. So did you ever hear like on the news, they say, hey, what's the chance the stock market's gonna go up or down tomorrow? How can they know that? Well, they kind of look back at other data and say, oh, based on other data, we think it's probably gonna go up tomorrow. Right? But it's the same thing as predicting the weather. It's just too complicated for us to nail down. Right? If we were able to nail it down, there'd be no speculation of that kind of stuff. People would be making money or losing money. Okay, what else do we need to look at? So usually I use the symbol P for some probability of something happening. It's a fraction, right? And it's the favorable outcomes over all outcomes. You can't have more than everything. Okay. So what's the chance I'm going to flip a coin and one side will show something? I mean, I'm going to say head or I'm going to say tail. I'm going to see something, right? So there's a 100% chance of that happening. So probabilities can be at most 1 or 100%. What's the probability I flip the coin and I will see neither a head nor a tail? 0. I'm going to see a head or I'm going to see a tail, right? So on the low end, something can have a probability of 0. So probability has to be between 0 and 1. 1 is the same thing as 100%. 0 is 0%. A lot of times we use words like likelihood or certainty. Can't be 120% certain something will happen. The most you can be is 100%. Are there some times when percentages can go over 100? Yes, but not in probability. This is one of the cases where 100% is the limit. You can't go beyond that. Because that means it happened. What's the probability it's snowing in this room right now? 0, it's not snowing in this room right now, right? We have a roof. I've never seen precipitation come in the middle of a room like that, right? What's the probability we're attending class right now? 100%, okay, yeah. So you can have probability of 0, you can have probability of 100. Usually it's somewhere between there. Next big idea with probability, the law of large numbers. So this is a law that relates theoretical to experimental probabilities. And the large number we're talking about is the number of times you run an experiment. So if n is the total number, sorrow, I think I might need to get some new technology. Number of trials. Remember, trials is another word for experiment. So it could be flipping a coin over and over again. It could be shuffling a deck, drawing a card, looking at it, shuffling a deck, drawing another card, looking at it. It could be rolling a dice and looking at it. It could be shooting free throws. It could be checking to see whether it snowed at a certain time each day. So you run some experiment over and over again. You observe what happens. And the deal is, as n gets bigger, the experimental probability, so I'm going to call that EXP prob, gets closer to, hang on, shrink some stuff, shift it out, oops. The experimental probability gets closer to the theoretical probability. So if I flipped a coin 1,000 times, I would expect to get close to half heads. The more I flip, the closer I should get to 1/2. So if I did it a million times, I would expect the ratio of heads to a million to be closer to 1/2 than if I did it only 1,000 times. That's basically what the law of large numbers says. So just because we have a theoretical probability, that doesn't indicate what's going to happen in reality. So a variety of reasons for that. We have what are called independent events. So I flip my coin, it lands on heads. Now, I'm going to flip it again, and the coin knows it was heads the first time, so it will do tails the second time, right? No, there's nothing like that in there. Each flip is independent of the other flip. Okay? So events are independent if one trial doesn't affect another trial. So examples of events that are independent: coins, dice. You think about a free throw. I shoot a free throw, I get it in, I shoot a free throw, I miss, I shoot a free throw, I get it in. Jackie thinks they're not independent. What's that?
Each like free throw is not the same as the other because you might get tired.
I might get tired, maybe I get more confidence because I got one in. Whoa, what happened to the screen?
You have a memory of how like the previous trial.
Yeah, so sometimes it seems like an event could be independent, but maybe not. So the free throw is a tough one. I would say it's probably not independent. It could be they are dependent. Like I miss and then I get nervous. I start sweating, shaking. Oh, I can't even throw the ball, right? So, and then people talk about streaks in sports. Okay, I think the statistics show that streaks are kind of a myth, but people seem to have them, and we get all excited about them. Okay. Cards, yes and no. Okay. So a card deck dealing the cards would be independent only if I look at the card, put it back, shuffle it, look at the card, put it back. But if I hand the cards out and don't put them back in, I'm changing the denominator each time. I started with 52 cards, but I gave Sarah one, now I only have 51. Right? So the chance that Jackie gets a red card is no longer 1/2 because there aren't 52 cards. Okay? Regardless of whether Sarah got a red card or not. Okay? So, so I'm going to write cards in this list with replacement. What that means is I replace the card back into the deck. As long as I do that, playing with cards is independent. But generally, if we're going to play poker, I'm not replacing the card back in the deck. You get to keep your set of cards. That means they're not independent, the probabilities. So calculating things like poker hands is pretty complicated because every time you dish out a card, the probabilities shift a little bit because your denominator and numerator changed. Okay. And those are harder to count. So, but if events are independent, then hey, that makes things easier to do. If they're not independent, it's a little trickier. That's okay. So, if events are not independent, then those are what are called conditional probabilities. And the condition just basically means, hey, something happens, and we have to take into consideration what happened. Like I dealt a red card, or I dealt a card, I don't know which one. So independent events relate to conditional probabilities. Examples of that are pretty much almost every other kind of probability out there, except for easy things like dice and coins. So classic examples are cards without replacement. Right, so just think about the red card thing. So I deal a card, right? Either that card is red or that card is not red, right? If I only care about red for a sec. Okay. How many cards are red? Well, 13 out of 52 cards are red. How many cards are not red? Oh, sorry, 13. 26. 26 out of 52 are red. 26 out of 52 are not red. Okay. So let's suppose I dealt a card, we looked at Sarah's card, and we saw that it was red. That means we're on this version of reality. And now I'm about to deal out another card to Jackie. Right? Either the card is red, right, or it is not red. True? Okay. So we know we dealt a red already. So what's the probability the next card is red in this chain of events? Well, there's only 25 red cards left at that point. And there's only 51 cards in the deck at that point. And so we can make a tree branching process to kind of think about probabilities. The not red, well, I know she got a red, but I'm looking at not red, so there's still 26 not reds, but there's 51s. Right, so that's what that second branch would look like. Down here, card's either red or it's not. I dealt out a not red card, so how many red cards are left?
26.
There's still 26. And there's 51 cards because I'm in the branch of reality here after I dealt one card. How many not reds are left in this branch?
25 out of
I
50.
dealt one not, yeah, so there's 25 of them out of 51 not. Yeah. So we can pause and think about that. So we'll do more practice drawing trees like this over the next couple of classes.
You've done 2 cards?
2 cards.
So it should be over 50.
No. This is my second card right here.
Oh, yeah, so, but.
Yeah, so
what
this
is
is
that
me
show?
dealing, these are the possibilities for the first card. And which color?
Oh,
And
okay.
these are the possibilities for the second card.
I got it.
So if I deal 2 cards and I'm concerned only about red, there's 4 possible future events.
But
Okay?
then the next.
Either there was a red, here are the possibilities, ready? The possibilities are, if I look at my tree, that it went red, red. This branch over here is red, not red.
Okay,
This branch over here, I got a not red first, and I got a red second. And this last branch means I got red, then red. Those are the 4 ways I can deal 2 cards only thinking about red. Forget about all the other suits, right? You see what I mean? If probability is only about counting, it's like, man, I can count. I'm a pro. I've been doing it since I was like 4, 3. But sometimes the counting is pretty hard to organize. And so this is pretty advanced. We'll come back to this later. We're going to do some simpler versions of it now. Okay. So I'm going to do a simpler version of this right now. So we're going to go back to independent events because they're easier to deal with. I'm going to go to dice. No, let's not do dice. We're not ready. Let's do coins. Okay. So the experiment is to flip 2 coins. And just make a note of whether there was a head or a tail. Okay. So I'm going to ask a bunch of questions about this, and then I want you to kind of play around and see what you can come up with based on what we've done so far. So one question might be, what are all the outcomes here? And I guess I should be more specific. What I really mean are simple outcomes. Other things I might want to know is like, what's the probability of getting 2 heads? What's the probability of getting only 1 head? And maybe that's a 3 and 4. What's the probability of getting no heads? All right, so I just want to let you guys play with those ideas for a minute. So whenever we list all the simple outcomes, that's called the sample space. You'll see that in the homework and in the book. Sample space is a list of things that can happen. The list of things that can happen is based on the experiment. So make your best guess at what you think the simple outcomes are. And guess or reason or calculate each of those probabilities.
How many total?
So we're thinking about this
flip
as
2 coins
I'm
at
flipping,
one time.
I'm flipping 2 coins, yeah.
Oh, okay.
And then we're trying to reason through this with the idea of theoretical, meaning we believe certain things about the situation, we think we know everything. So this isn't something we're going to do 1,000 times. What's the possibilities? Flip 2 coins, what could happen? Let's make some guesses. Anybody want to guess what they think the probability of 2 heads is?
50%.
50%? How about what's the probability of getting only 1 head? 50%? Okay, what's the probability of getting no heads? Okay, so let's pause and think about that for a second. Is this true that either I'm going to get no heads, or I'm going to get 1 head, or I'm going to get 2 heads?
Yep.
Okay. And what's the maximum probability one can have?
4 different ways.
100%?
Yeah, but
Hang on one sec. I'll let you see that. These add up to 150. So something's wrong there. Because no heads is a different thing than only 1 head, right? Do they have anything in common? No. Having no heads is very different than having 1 head. Only 1 head. Having 2 heads means I have more than 1, so it's not only 1. Okay. So these are what are called mutually exclusive events. I don't know if I call them simple events. I'm not ready to say that. Sarah?
I did something
You
weird.
think you said 4? There's
Yeah,
4
because-
outcomes?
I'm strange because I wrote out all the outcomes it could be. So I did
Okay.
like HH for 2 heads, TT for 2 tails, and then I counted them all up.
Okay.
And then I tried to find the fraction or the percent of the probability out of
So,
that.
so what's a simple outcome? One possibility is the first coin was head, the second coin was head. That is a single simple event here.
Then I did tails,
It could be tails.
and then I did, it could be head first or tail first, and then I did it the opposite because
It could be head then a tail, but it
And
could
then
be
a
a tail
tail
then
and
a
a
head.
Yeah.
Okay.
But
So
that
yeah,
doesn't matter.
really?
If you're just flipping it, I thought you were flipping it at the same time. And
So
then there would
sure,
be
I'm
a
flipping them at the
first-
same time. Okay. So you think these two are the same event?
If you're flipping it at the same time.
So we have 2 different perspectives on this problem. One perspective. Okay. So how many simple events are there in this version of reality?
Or,
There's 4 of them. Okay. And are you just as likely to get head as tail?
yes.
Okay. And are you just as likely to get head tail as tail head, or head tail as tail tail?
Yeah. if you're just
So I might believe in this case that each of these is a 25% chance of happening,
and that would be your 100.
and that adds up to 100%. So that feels safe. Okay. Jackie's perspective is either you get 2 heads, or you get no heads, 2 tails, or you get head tail, which is the same thing as tail head, right? So this would be getting 2 heads, no heads, and 1 head. And then maybe it's a third each. It's a third plus a third plus a third. 1 whole, which is 100%. Okay. So either these are 2 valid representations of reality, or one of them is wrong.
Well, they're 2 different trials, completely.
Okay, so you think,
Because there's another variable of
Okay.
the sequence of flipping the coins.
okay, so I'm going to experiment with this in a spreadsheet. Okay, so let's bring up my Google Drive here, and we're going to run a computer simulation on this to see if that will help. Because it's going to be kind of hard to do this 1,000 times, and it's going to be pretty boring, right? But the computer can simulate this. It's a little weird, but I think it's reasonable. Flipping a coin is what we call a random event. Random events happen when probability is involved. Okay? So I don't know whether it's going to be a head or a tail. It happens. Oh, it's a tail this time, right? So that's the idea of random in mathematics. It's kind of complicated, but it's kind of simple on the other hand. So probability, close enough. And so I have, let's say, coin 1, and I have coin 2. So most spreadsheets have a random number generator in them, which is like flipping a coin. You could say 1 is a head and a 0 is a tail, maybe. So I'm just going to say, hey, can you do something random for me? And the computer says, yeah, I can do random between 0 and 1, or I can do random between anything. Okay, I'm going to go random between anything. And I'm going to say I want a random between 0 and 1. And so what happens when I run this command over and over again, it's either going to spit out a 0 or a 1. And since I only gave it 2 numbers, it's going to try to do it so that I'm as likely to get a 1 or a 0. So if I do this 1,000 times, I should see about as many zeros as ones. So it's like a coin flip.
What does that do?
Oh, the math behind it is very complicated. And people are always working to try to find a different random number generator. Okay, so just think about that for a second. You're going to be a random number generator. So remember, we have 10 digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So what I'd like you to do is give me a random digit right now. 3, 2,
6.
Okay, give me another one.
7.
Okay. Random. 2.
4.
Okay. 8. Give me another one. 1. 7. Another.
0.
Okay. And another 0.
6.
6. Okay. So was it hard to try and be random? Like, no? Yeah? Okay. What you find is if you ask humans to be random and you record all their random results, you're going to get a result that's not that as random as we hoped it would be. Like people are as less likely to pick 0 than other numbers. 7, for some reason, comes up a lot. People like 7. 2 is very popular. Yeah, so it turns out like Microsoft Excel is a spreadsheet. Like 10 years ago, I think it was, they got a lot of heat because their random number generator wasn't working quite right. It was giving numbers on the low end a little more often than it was giving on the high end. So its random number generator was slightly broken, and they had to do a lot of research to try to fix it because it was a big deal to some people. So I'm just gonna fill this down a ways. I think this is only going to give me 500. And if we run out of rows, then but I can always get more. Oh, it's going to go beyond 500. Maybe I'm going to get 1,000. Oh, okay. So I get 1,000 heads and tails there. All right. So if I'm only, let's say heads are a 1. So what I'm going to do in the next column is I'm going to go sum, and I'm going to add up those 2 numbers. Because then it'll just tell me how many heads I got in each row. Now, the other weird thing about the random number generator is every time you do something else on the screen, it reshuffles the random number generator. So stuff's always changing, which is a little bit freaky. All right, so I'm going to fill this back up to the top. Yeah, it's like binary in this case. Okay, I ran it too many times. Don't need that top one. And it keeps shifting. So then what I want to do is I want to know, well, how many, let's do it over here. How many times did like 1 appear over here? Let's see, is that what I want to do? Yeah. So let's see, I got none, 1, and 2 heads. Those are the possibilities. Okay. So equals, I'm going to count if, let's see, that's what I want to do. Count if, okay, that range is, I can just go 0. Okay. And then count if this range has a 1. Okay. And then one more. Count if this range of numbers has a 2 in it. And it keeps shifting each time. So this is interesting. Let's blow this up a little bit. How many times did I run the experiment?
1,000.
Almost. And I got a header row, so I did it 999 times. Almost 1,000. So if these were each equally likely, I would expect to see about 333 no heads, 333 times 1 head, and 333 times 2 heads. Okay, is 1,000 a large number? Yes and no, right? But the law of large numbers, it ain't large. Okay, so what I'm going to expect is there's going to be some deviation. Okay. But this middle number seems about twice what the others are, doesn't it? Okay, and I can easily reshuffle this and get a new set of numbers. So what do we have? We have, let's copy those over. Paste values only. We got a slightly different set of numbers here, but are they still in the same ballpark?
Yeah. Somewhere
in the 200s, almost 500. And every time I do something else, like type something on the screen, it's going to reshuffle those numbers. Okay. So either the random number generator here doesn't work well, or it does work well, and getting no heads, 1 head, or 2 heads, those aren't equally likely. So Jackie was thinking of it that if we flip them at the same time, there isn't a difference between getting a head and a tail or a tail and a head. But there is a difference because you have 2 different coins. Name them. Let's call one of them Fred and the other one George. Okay? And we always look to Fred first. And you may say, that's not fair. Well, fine. We'll always look to George first. Okay? So even if we flip them on this at the same time, here's what's happening theoretically. One of the coins came up with a head or a tail. Maybe it came up with a head in this universe. The other coin gets to be a head or a tail also. In the other universe, it got to be a head or a tail. So this tree shows me the 4 possible outcomes. If I follow the branch from origin, line from origin to end, then this is going to show me that one possibility is head-head, another possibility is head-tail, another possibility is tail-head, and another possibility is tail-tail. And it doesn't matter whether I flip them at the same time or I flip one coin and then the other coin. Turns out those are exactly the same thing. Even though it feels different according to time, according to observation. And what's the probability of getting a head? 1/2 or 50%, right? So this probability is 1/2. Probability for this other coin of getting a head? It's still 1/2, right? So every leg of this tree has a probability of 1/2. And if the events are independent, when you follow through a branch like this, you get to multiply those probabilities. 1/2 times 1/2 is 1/4. 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 Next one there. So there's a couple different ways to think about it. Because these events are independent of each other and they happen consecutively, I can multiply their probabilities. The other way to think about it is because they're independent, as I'm moving through the tree and the head and tails are equally likely, I have 4 different equally likely branches at the end. Since there's 4 of them, their probabilities must be 1/4 each. Provided the original probabilities were equally likely and the events are independent. So we have 2 bits of belief that goes into that right there. And every once in a while, I do something like this and I have a doubt, like, I don't know if I did that right. Okay? And so sometimes experimenting with a computer, random number generator, can help me troubleshoot if I was thinking through it right. And this computer troubleshooting seems to indicate that 477 or 492 out of 1,000, that's about a half. And 270, 260, 250, 240, that's about a quarter of the 1,000 flips or 999 flips I did. So these are experimentally coming out to be what this tree says. And just double check what the tree says. The tree says there's two different ways to get one head, right? This way gives me one head. This way also gives me one head. Their probabilities are a quarter each. A quarter plus a quarter is a half. So what I should see when I run this experiment, that half the time we'll see only one head. A quarter of the time we'll see two heads. And a quarter of the time we'll see no heads, is what ends up happening here. And a tree is one way to kind of troubleshoot those ideas. Random number generators, computer are another. You can also make tables. So let's look at this as a table, and then it's time to play with our activity. Tables. So with a table, what you do is you can do a table when you have two different things happening together. So we have coin 1 versus coin 2. And coin 1 could be a head or a tail. That gives me 2 columns. Coin 2 could be a head or a tail. That gives me 2 rows. So coin 1 could be a head. Coin 2 is a head in that cell. Over in this upper right cell, coin 1 is a tail. Coin 2 is a head. Lower left, coin 1 is a head. Coin 2 is a tail. And lower right, coin 1 is a tail. Coin 2 is a tail. So whenever you have two things going on, you can usually make a table to analyze it. You can always use a tree. The table gets a little more challenging if you have 3 or 4 different things happening at once, but so does the tree, because the tree gets bigger and wider and more detail on it. So bottom line, probability is about counting. We have to find some way to count and make sure we keep track of everything. And it's easy to have our beliefs be wrong or misleading, like with that example of flipping the coin and flipping them both at the same time. It turns out it doesn't matter whether you flip them at the same time or consecutively. It doesn't even matter if it's a single coin. Flip the coin once, look at it, flip the coin again, look at it. And it turns out that's all the same situation.
So then it only has 3 outcomes, 3 possible.
Something that only has 3 outcomes. Something that comes out with 3 outcomes.
3-sided dice.
Yeah, it's a hard one. 3-sided dice. Oh, hang on. That brings us to our next topic, spinners. All right, so I'm going to bring up the spinner experiment. Perfect, Jackie. You totally led us into this.
You know how long I stared at that circle with the thing in the middle of the big round.
Okay, so we're going to embark in just a moment on activity 1 in chapter 9 of the workbook. And I have these things, and we have these plastic spinners we're going to grab in a minute and put on top of there. You could also make your own spinner at home by just putting a pencil point in the middle there and getting a paper clip and sticking the pencil through that little hole in the paper clip and flip the paper clip. Wonderful homemade spinner. Works great. Okay. So this circle was designed so that there's 3 regions. From the center, each region has the same amount of, say, degrees rotation for each one. They're each 1/3 of the circle from the center. So if I spin a spinner on top of this, in the first spinner A, I'm just as likely to get a 2 as I am a 4 as I am a 9. You with me? So this is a situation where getting a 2 has the same probability of getting a 4 as getting a 9. So for spinner A, what's the probability I get a 4? 1 out of 3, or 1/3. Okay, 1/3 is a little messy as a percentage because the decimal goes on forever, right? But we could say, yeah, it's about 33.3%. Close enough. So for activity 1 here, we're going to run this experimentally. And we're going to check a couple of things, and so we're going to have to record data on it. So these tables are kind of the same, but they're kind of different. One of you is going to do spinner A, so you're going to match up in just a minute, and the other one's going to do spinner B. So if you're doing spinner B, you're just going to replace where it says number on spinner A with spinner B. Okay? And then you'll replace the 249 with the 357. And you just want to keep track of, well, how often did 2 happen? How often did 4 happen? How often did 9 happen? And we're going to do this 30 times. Right? To a human being, doing that 30 times feels like a lot, right? But for the law of large numbers, it ain't a lot. Okay?
What happens if it ends up in between?
Then you make believe that didn't happen.
Okay.
Yeah. It's always going to lean to one side of the line.
Okay.
Okay. And if you zoom in with a magnifying glass, you'd be able to referee that. Okay. But if you guys can't decide which side of the line it is, just don't count it and do it again. Okay. You also want to keep track, and these, it says tally marks, so every time it hits that, you just make a mark, make a mark, make a mark, and then we'll count up the tally marks after. And that's what frequency is. Frequency is how many tally marks were there? Were there 10? Were there 9? Were there 15? Okay. And we also want to keep track of spinner A versus spinner B. Now, this is organized here as a nice summary of it. You could write it down in a slightly different way. So I'm going to go back here. So we've got this spinner, and we have a spinner A, and we have a spinner B. And let's see, spinner A had, was it 2, 4, and 9? Correct. And spinner B had 3, 5, and 7. Correct. And the order doesn't matter, I'm just going to do that. So another way to keep track of this data would be to have which trial it is, what happened to spinner A, and what happened to spinner B. So for example, I could spin spinner A, first trial, and spinner A got a 2, B spun and it got a 5, and I can clearly look at that and see who the winner was. Okay, so this would be another way to keep track of that data. So my recommendation is that instead of keeping track of it the way the workbook authors recommended it, we actually make a table like this, and we write this down so we see all 30 of our trials and which number popped up. Okay, so you can have one of you guys be the note taker for that, or both of you. Sarah?
We can't find a pattern with probability.
What do you mean you can't find a pattern with probability?
When we were in chapter 1 doing all the patterns and everything,
Yeah.
after a certain amount of time you could see a pattern. How come with probability you can't?
You're gonna have to show me a problem you're referencing, because I don't. You mean a problem in the decimals, or?
Just from before, like if we spin it 30 times and each time we get a 2. Let's just say
so this is,
assume that would be a pattern?
so what the spinner lands on varies, correct?
Correct.
So that means the result of spinner A is variable. And it involves chance, so it's called a random variable.
Okay.
So with random variables, there are patterns and there are not patterns both at the same time.
Okay.
So for example, is it possible to spin spinner A 1,000 times and never get the number 2? Yes, it's possible, but it's extremely unlikely, right? It probably won't happen. Another thing is there are because of the way events can happen and the 1/3 probabilities, you should expect to see a certain number of 2s. Not only that, is patterns also pop up into how many times, like getting 2 in a row. Like you get a 2 and then a 2 and then another 2. So if I did this 1,000 times, I would expect to see some long runs of 2. Or 3, or 9, or whatever the number is. Okay. So for example, there have been cases where fraud has been detected because people were randomly, in their own head, randomly putting numbers in spreadsheets for a company. And then later when somebody reviewed the books, they said, wait a minute, these numbers aren't random enough, right? And it turns out you can make predictions about, in 1,000 entries, how many times do you expect to see the number 2? Okay. Even in a business setting. And so you can use ideas about probability to kind of detect fraud, which is kind of wild. Anyway, okay, so it's time for you guys to run the experiments. I am going to stop this recording.